Hello and welcome to another reverse engineering video. In this one we'll be looking at one of the challenges from DragonCTF that was held last weekend. The challenge name was retrozeit. It wasn't very difficult, it's difficulty easy. It was solved by more than 16 players, but it was quite fun. Unfortunately, it was the only challenge during this CTF. So we'll look how it could be solved. And as usual, we get some description. Just wait for the flag, works on AmigaOS 3.x, workbench. And of course, we do get our file. And if we run file command on it, we'll get info that yes, in fact, it is recognized as AmigaOS, load sec able executable binary, BLE. I don't know, big little endian binary. So what we can do, of course, we can load that file into ghidra, but before we do that, we have to prepare ghidra, because if we don't, ghidra will not recognize this file. It will be recognized as raw binary, and this is not really raw binary file. There are some structures inside and not everything is code, so we need to either understand the file and parse it correctly manually, or find something that can do that for us. And we can actually find something, and this is this ghidra Amiga LDR from lab 313RU. And this actually can parse this file and can indicate to ghidra specific structure and specific memory maps can be prepared by this extension, and we are good to go to actually start reverse engineering. We don't have to worry about the structure of the file. So to do that, you need to download the release. It's a zip file and it can be added to ghidra. And to do that, on this panel, you just need to go to File, Install Extension, add this extension here, and then after restart, this file will be recognized as Amiga file, and everything will be in place and the file could be loaded correctly. And with that, we actually get a lot of extra information in ghidra. So for example, the memory maps are set, a lot of functions are being recognized. All those exec functions, we didn't have them before, they are recognized here, and some strings. And we even do have the start method recognized, so we know where to actually start with the analysis of this file, and that really helps. Without that, we would have to understand where the code starts and how is it mapped in memory, and everything is done by this extension. So really good extension and really speeds up the analysis. So having this file loaded into ghidra, we actually can go to strings, because there are some strings that can indicate what's going on. Actually, also we could run this file in one of the emulators. Actually, I did run it during the competition in one of the emulators, but it didn't really showed me much. There was info that it's calculating the flag, and actually I think the emulator restarted. I don't know if it's on purpose or not, but there was a restart. But here we can see, okay, there's calculate the flag will show up here, and calculating the flag. There is some other text that might be interesting, but there's not that many. But we can go to one of those, either calculate the flag or calculating the flag, and work our way from there. So I go to calculate the flag. Actually, I can see it is being used in this initialize. This method wasn't called initialize. Of course, I called it like that. But we can see that there's quite a bunch of code. We don't know what actually it does, but we can see some information that looks quite familiar to us. We have this calculating the flag, and of course, when we see the string, we could rename this function to some sort of print. Probably it should be print the string, not print the flag, but it's some kind of print instruction. We can see there are some send IO function being called, and you can see some more printing, like here, print calculating the flag, and we can see some function that was identified as a malloc. So we allocate some memory, we do some more of the calculation or some sort of operation on the data. And here we can see that we are assigning flag and semicolon, or actually colon, to something on the stack. We also malloc something, some more memory. We do something interesting with this memory, and then we again call this function print the flag. So we can assume that some interesting stuff is being done here. So printing the flag, of course, it is assumption that it actually does print the flag. We don't know, at least I don't know that, because I'm not that familiar with Amiga operating system and reversing the binaries for that, but we can safely assume because of the usage of this function with, for example, here the string and also here with the string. So the assumption is that it actually prints stuff. So we can think of what this interesting function actually doing, because it gets past some data. And if we look at this code, of course, it's a bit cleaned up. We can see that, okay, we are XORing the data at this encoded flag memory address. Of course, I renamed it to encoded flag, but there are some data here, and we XOR it by the index of the byte. So we could assume that's our encryption algorithm, but that's not actually the full picture. If we just try to run it, we won't get correct data. We won't get correct data because this encoded flag is actually being changed before we actually reach this method. So here we only do the XORing with the negation of the byte, but that's not the whole picture. We see here a lot of xrefs are being done to this memory address. And if we go to those methods, we can actually see that the encoded flag is being used in some other method that looks quite interesting. So there is some kind of loop, and we get some random values. We calculate modulo hex 27 because that was the length of the flag. We get two values, and then if they are not equal, we will shuffle the bytes. So the bytes in this encoded flag will be changed in place with and based on this shuffle array. And the shuffle array is here. So it's like 16, C, 24, 17 hex values. And based on that, we will shuffle the bytes in this encoded flag. So that's why I said that it's not enough just to mimic the algorithm in this interesting function, because if we do that without shuffling, it won't be correct, because of course bytes won't be on the correct position. And so we need to find out how the shuffling is going. And since it's a random function, of course it's a pseudo-random function, we need to find out what is the seed of this random function, because without that we won't be able to get the same results and get the same values for I and j, and without that we don't get the correct flag. And how do I know it's a random? If we go to this function, we can actually see some specific constants. So this hex 41C64E6D and this 3039. If we look at that in DuckDuckGo, we'll see that this is like a common pseudo-random algorithm for generating the pseudo-random values. We get some seed and we multiply it by this value and we add the second value. But the problem is that in this binary, if we go to seed, the seed is set to 1. And actually it's not being modified anywhere in the code. And of course, it's not that easy, because if we use 1 as a seed, we don't actually get correct results. We will get some garbage and the flag won't be readable. So how we can do that? One would be we could try all the values for the seed and hoping that it's not really big, so we'll get the hit quite soon. But yeah, I tried that and it's not, I guess, possible. I'm not sure if it's even possible if you run the whole spectrum of the values. I think it might be that no value of seed can provide us the correct order of the bytes. But there is one additional function in this binary that can give us a hint how the bytes in this shuffle array should be placed to get the correct flag, and how to obtain that information. If we go back to either here or the other method, actually here, so if we go to here, we can see, okay, here based on the shuffle, we shuffle the bytes. But if we go just to the shuffle and we see the xrefs, it's being used in those places. That is correct, but I'm looking for one more. Yes. So shuffle is used in those places, but we can see that there is like a usage of not only the start of this shuffle array, but also to the second byte, third and fourth. And it is being done in this method that I called shuffle. I didn't really know what it's actually doing until I realized what it's actually doing. And if we go here to this shuffle, and if we look at this function, it's might be a bit hard to read, but if you look closely, this actually checks if the bytes of the shuffle array are in correct order. And we can confirm that if we go actually to where this function is being used. So we go to initialize and we check. So basically here we call this shuffle and we get the result. And only if the result is 0, we will do the rest of the function that are interesting to us, like decode the flag. So this is like a guarding function. So if we'll get correct result from the shuffle, and only then we will decode the flag. So we can know that the shuffle function gives us information how the bytes should be, what should be the order of the bytes in the shuffle array to get the correct flag. And of course, when I say in shuffle, that also determines how the bytes will be in the encoded flag, because when we run this shuffling of the bytes, we'll get also the bytes in the flag will be mixed. So let's look closely here, and it might be a bit hard, but it's like two parts. So the first part is for the even data, and the other one is for the odd data indexes, and it basically guards that the values of the values at index 0, 2, 4, 6 and so on are in descending order. So basically if they are not in descending order, we'll return something that is not 0. So basically the indexes at 0, 2, 4, 6 and so on has to be in the descending order, and for the odd indexes it has to be in the ascending order. So it has to be at index 1 has to be lower than an index 3 and 5 and so on and so on. And basically it checks all the shuffling array, and thanks to that we know what would be the indexes actually for all the values, because we need to put them in that order. So this function is satisfied, and it is satisfied only when even indexes, values at even indexes are descending order, and at odd indexes values are in ascending order. And based on that, we don't have to actually guess the value of the seed. We don't actually need the seed. We just need to change the values of those arrays so that they are in correct order. So let's just see how it looks in the code. So this is my very best solution. So I actually tried with this random function, but then I came up with the ascending descending order of the indexes, and I didn't really need that. But I have this interesting data, I have a shuffle. I just cut down the interesting data to 27 hex because I think I copied too much at first, but maybe then I cut down to actually 27 bytes. And then we just need to sort them in correct order. So actually shuffle. So I'm just like going through half of the indexes, because I will just deal with the even ones and then odd ones. And I'm like searching for what is the index of value m. So like 38 is the highest value, and I'm searching for that in this array, and then I'm replacing at index 0 value with the value at where value 38 is located. And this is basically the same code that we saw in this shuffling method. Here it's just like I'm not generating any random numbers. I know where the number should be. And the same happens for the odd indexes, the same algorithm, just different j and m. So here it will be ascending order because I'm adding to m. Here I'm decreasing m by 2. And after that, there's not that much we have to do. We just need to mimic the XORing with the byte negation algorithm and just append characters to some array and just print them. So that's actually all that needs to be done for this challenge to work. So we didn't have to really do anything with the random. We didn't need to find the seed. That was my first impression, that I do have to find the seed, but I don't think any seed would work. I did try to run, and even after solving this challenge, try to find out what is the correct seed, but I don't think there's any correct seed. At least, I couldn't find any working one. But so let's see how it works, and let's see what the flag is. So if we run this, so actually it decrypts, and the flag is Dragon sector. You could have just waited, and I don't know whether we could. I didn't wait for this to finish, but nonetheless, the flag is ours, and that was quite fun challenge with Amiga is not very common target. So I hope you learned something, and if so, please like and subscribe, and see you in the next video. Bye bye.